Hey guys, welcome to the stream. Hello. Welcome to the Atlas breakdown stream. So those who don't know, 2 weeks ago was the revision demo party. Myself and Nobi worked on a 64K intro called Atlas, which came third, which was really awesome. And I guess today we're gonna look at some of the details behind how it works, go through and I guess deconstruct it and just like chat about it, I suppose. Yeah, so welcome to the stream. What is the chat there? Wow, lots of people. Hey, Jables, Daniel Cohen, Procyon, Luna, Velocitira, Nobi, Twistertube, Gugito Efeme. Hello, welcome. So, I mean, I guess we should get started. We'll just watch the intro, so you have a bit more context if you haven't seen it yet. So, I mean, we'll do that. I will just mute myself and you can just get this, yeah. Let me get this big. There you go. And you can enjoy the stream and then we'll get right into it. So here it is. Cool. So that was the intro that Nobi and myself presented at revision. As I said, it came third against very tough competition. So I was really, really proud of that, I think. And I'm quite happy with it. Let me put a link to the Puit page in case you want to download it or watch the full thing in YouTube in high res. There you go. So, I mean, I guess let's start with the obvious. Unless there are any questions before we dive in. No. Cool. So, yeah, we'll start with the obvious. This is the tool, or the mini tool, as I kind of call it. It's a bit bare bones, but it does its job. So I developed this in about 2 weeks, specifically for working on a revision entry. 2 weeks, considering I'm a uni student, I have way too much free time. So yeah. But there's lots of rough edges, so it was very quickly done. Yeah, and using ImGUI. So initially, myself and the other Monad people from Australia were going to do an entry for revision, but a bunch of things happened and that didn't really end up working out. And that's what I initially built this tool for. But then at some point, I think about a month before revision, I messaged Nobi with an idea to do this kind of rocket thing, and I think he was all in for Ocean. I'm a uni student. I'm not doing very many subjects, so I have a lot of free time. So yeah, so this is that tool that I built. Basically, we have preview window there, profiler, which is very, very handy for debugging stuff. Timeline here. In the timeline, there are 2 kinds of clips. So these green clips are generators, and then the grey clips are animations. So I'll go into that a little bit more in a minute. Down the sidebar, we have the list of all the properties. So each generator clip has certain properties that it can expose that you can edit in the editor. And all of those properties can be animated in animation clips. So you can see here, like, this world light has, a direction, a color, an ambient amount. I don't think that's actually going to change anything in this case. The camera has like a position and direction and things. Skybox doesn't have any properties. There's stuff like the terrain properties, like you can do it with the terrain. But we'll go into how actually everything's constructed in a bit. There's, like color grading and bloom and post-processing and stuff as well here. So so then we have animation clips as well. And they're basically comprised of a bunch of motion curves. So each animation clip is tied to a generator clip. So say this fade, is tied to the grading. It says on the sidebar here. So the fade is tied to the grading clip, and it's affecting the fade and the gradient A properties, which are this fade and this gradient A. And then we have like a bunch of keyframes which we can kind of like move these around, and we can change how the curves look and everything. I mean, tool-wise, that's basically it. What's the yeet parameter? That's the secret sauce. Just the chromatic aberration that we didn't use. Logic chroma. No, but we did use this chromap, which is just a color separation. Oops, that's not what I meant to touch. Novi, it may or may not have existed prior to today. What was the grain? Yeah. But we do have this chromap parameter, which I just turned up heaps, which is much cheaper. But we will look at the post-processing a bit later. So, hey Akama, welcome. Hey, everybody else. how you'll do it. So I guess let's go through each of the scenes and we can do a bit of a high level overview. I don't really have a structure or a plan for how to do this, so we'll just kind of go along and do it. So basically the order of the scenes that we did was back when I first talked to Nobi about it, I was working on this scene, which I guess you could kind of say is our main scene. And this was based on a picture. Let me just find it. It was basically I decided to try and replicate a picture, a reference picture that I liked, and just see how it turned out, and it turned out pretty well. So it was this, which is a picture by, I need to actually see who it's by. I'm just looking up on my laptop because I do want to credit it because it's beautiful and I like it a lot. If I can find the picture. Anyway, I will find it later. But this is really nice. So my initial goal was to duplicate this. Yeah, I could just reverse Google image search. You're right. I'll do that in a minute. Oh, Luna. No, it's not a fluid sim, but I'll go into that later. So I wanted to replicate this, basically, and to see what happened. And I will show some of kind of the work in progress things from that. So the first goal, of course, was to make a nice looking volume renderer. And I had been working on a volume renderer for what our 64K intro was going to be before I worked on this one with Nobi. And that would basically get results like this. Oh, hang on, that's not moving. Kind of look like this. So there's a volume, there's a directional shadow, pretty basic. Yeah. And that was really great. So, I really liked that, but it was missing two things that we needed for this scene. One of which was proper scattering, multi-scattering, which you really need to make your clouds look good. So you see like these clouds here, the light's kind of scattered through it and diffused a bit and then came out. And also point lights, which is like, the rocket source. I'll go into why those are both difficult in a minute. But first, this is when I got point lights working. So you can see there's a point light and we can move it through the shadow volume. As you can see, and then this is when I started getting multi-scattering. So you can kind of see that there's a lot of diffuse light kind of bleeding through the cloud, more so than just with direct lighting. And then this was the first, I think that this was the shot that I originally sent to Nobi, and a couple of other people, which is a directional light and a point light, and then a bunch of clouds. Yeah, and so, we've got shadows and everything. And this basically is what ended up morphing into this scene. Just this has, a lot more colors or color adjustments and like a proper shape of the world, and the rocket, obviously. But this was basically the starting point. So here's another part of the tool that we have, which I should probably explain before we get started. In this preview window, I can click on it, and then I can like move around and look around like an FPS. So this is the scene. It's all this little tiny box with a tiny little rocket, tiny cute little rocket in there, and the sunlight. Yeah. So there is the illusion. You'll never be able to unsee it. So basically what's going on here is this whole kind of world is 3D texture. So it's a 3D map of densities. So within this map, each cell has a density number. And then to render that, we start from so we shoot rays out of the camera at each pixel. And first we do an analytical ray trace, basically to see where does the ray intersect with the volume. So with this box, which in our case, when you're inside, it's basically going to be all of the pixels. All the pixels are going to intersect. But for other places where we use volume rendering, that's not always the case. So once we find where it intersects the box, we then step through the box. So we have a certain number of steps, or a certain step size, I think in our case, and we just step through. So we have a point, and we keep shooting the ray incrementing by those steps. And each of those steps we sample from the density, and then we do a bit of maths to accumulate that to get kind of the final density that goes through the ray. So so that's how you can get basically a basic density kind of thing, but that's not going to have shadows in it. So if I wanted to, I'm going to dive into some shaders now, and I'll show you what that looks like if we just do that and we don't show some clips of this stuff, which would be this. So we're stepping through our volume and accumulating density, but we're not actually shading it, and it looks super plain. And if I reset the camera back to be inside the volume, it's just grey, and that's very boring. So obviously we need lighting, and lighting through a shadow volume or through a density volume like this is complicated because it's difficult to do quickly. Because if you imagine in your shader, you're already stepping, say, 100 steps, or I'm not actually sure how many steps this is, but I think, up to 256 steps. That's quite a lot. The naive way to do shadows then would be at each of those points, then start stepping to the light, and then determine, okay, how occluded is the light from this point. And that works, but that is insanely slow, and it's not going to be real time, let alone 60 FPS. So in this case, the scene is running at 10 or 8 FPS on a 1080. So that doesn't work. So what we do is a technique called deep shadow maps. And this is when I get paint out, because paint is where all the good stuff happens. So we know we have this 3D grid that has the density. And we know, since this is a directional light, so the sunlight we treat as all of the light is coming from a plane, so it's all just coming down in one direction, so it's a directional light. What we can do, so normally if we're marching through our volume, and then at each of those positions we march to the light, while we're marching to the light, where we're sampling, it's not necessarily going to be in the middle of a cell in the volume, so we have to do filtering around the cell to basically interpolate. But we can take advantage of the fact that our light is entirely directional and precalculate that shadow amount by making another 3D grid and orienting it so that one of the axes faces towards the light. So that means that if you imagine stepping from any of those grid points to the light, you're going to be going directly through a column of the texture. So we can build that texture by just stepping through 2D grids. So start with the grid and then do another grid and another grid, another grid, another grid, and just cascading the values down. And that's really, really cheap. So that's really easy to do. That's called a deep shadow map. So if you imagine we have a volume, this is our deep shadow map. So in this case, we're saying that the sunlight is up here and it's looking straight down. So we have our shadow map is aligned so that the z-axis faces up. And this is going to be, this is a grid. So just imagine this is filled with cells, right? Like so. So what we can do, so then we have this, and then we also have our volume grid, which is also kind of pre-calculated. So that's what we're actually stepping our rays through. And so what we can do is we can run like a compute shader on this, and we've just run it for each of the cells in a 2D plane. So we have our volume, we just do kind of say the top plane. And what each of those does is it starts at the top and it calculates the density here, and then it loops down to the next one and it calculates how occluded that will be, and then it loops down to the next one and it does it again, loops down, does it again, loops down, does it again. So imagine if you have a shadow volume that's 128 by 128 by 128, each of those kind of compute iterations is going to have a loop that runs 128 times that just cascades down the volume. And that's actually really, really quick, because you only have, in each of those loops, you only need to do a single read from the density map. And all of the threads, so in a shader, because of how GPUs work, you want all of your threads to roughly be doing the same thing. So if you start having like branches in them and all kinds of stuff like that, then they start to diverge, and that's really bad for performance. But in this case, so say we're doing our march to the light just in that naive approach. So at every position in our march through the volume, we also march up to the light. Then each of the cores is probably going to be in a different state along there, because it's going to be doing a different number of marches and things to the light. Whereas here, every single thread, so every single shader thread is going to be doing exactly the same thing. It's really, really coherent because they're reading around the same place. It generally just is nice to the GPU. So once we have the shadow map, then when we're actually marching through our volume, at each position that we march, we can just convert that position into the shadow map's coordinate space, and then look up what the occlusion is at that position, because that's what's stored in the shadow map, and then use that, multiply that by the intensity of the light, and that's it. So if we go back in here, that would be this. Actually, it wouldn't be, because this also has multi-scattering, but roughly that's what's happening here. So you can see here, this add sample. So this is the shader here that's rendering the volume. So it's stepping through, and at each position, it's sampling from the density, and that sampling is what's happening here. Hey, Guardian. So at each position, you can see here, so we're transforming our position where we are along the ray into the coordinates of the light map, or the light map, it's a deep shadow map. Then in the deep shadow map, we just look up the intensity, and then we multiply the intensity by the color of the light. And that's the amount of incoming light. And then we can just plug that into our, hey Ferris, how's it doing? We can just plug that into our stepping, and that just gives us the intensity of that point. And that's really all there is to it. So that works really well for directional lights. But one thing that we need here is point lights, which is this. And that's a little bit more of a trick. How do self-cast shadows work? So that's exactly what I'm talking about, Kogito. So basically our shadows are self-casting so when we build that shadow map, that deep shadow map, at each position we're accumulating the density as we go down. And so that means that each point it's going to be more occluded than the previous one. And so just when we read that, we know the occlusion, if that makes sense. I can show you a preview of what the actual map looks like, if that would help clear it up. It can be a little bit difficult to imagine, I think. But so basically the main property of these is that one of the axes in the deep shadow map is getting further away from the light. So in a directional light, you have the light, and then you orient your 3D, your deep shadow map, so that one of the axes, in our case the z-axis, is stepping away from the light. And that just means that you can have a loop in the shader that steps away from the light. So actually I can show that as well. We have the build directional shadow. So you can see here we're looping down the z-axis, and at each position in the z-axis we sample from the density, we just do some stuff to figure out how that would accumulate, and then up here we store that value in the shadow map. So it's basically just accumulating down each of the steps, down each of the layers. So that's the important part of deep shadow maps. So if we want to change this to work with point lights, what we can take use of is called spherical mapping. And spherical mapping is basically taking a world space coordinate, so if you imagine you're an x, y, and z, and converting it into a spherical coordinate, which is something like if we have our point light here, and I'll show this in 2D, but it can be trivially expanded to 3D. So the DSM is aligned with the light. Yeah. So if you go in here, we have this directional light field here, and I can change the position. So if I do this, you'll see it's moving. And it's going to be a little bit weird in this because I think it's only calculated once at startup. Because in our case, because the volume never changes, the directional light's never going to change. So you can see it doesn't quite look right. But yes, so this is the box that we're moving around that contains the directional shadow map. So spherical mapping, right? Imagine we have a point, and that's got an x and a y. What we can do is we can convert that point into what's called a polar coordinate, which is the 2D equivalent of a spherical coordinate. So what this requires is we need to have some origin. So let's we're just going to say that our origin is 0, 0 because that makes sense. So our point is a vector from the origin to xy. Alternatively, we can represent our point by an angle and some line length. So we can either do an x and y coordinate, or we could say an angle and a radius. So there are two ways of representing a point in 2D, which is those two ways. And you can, if you take note here, you'll notice that obviously that radius gets bigger the further we are away from the point. So that's the important property. The radius gets bigger as our position moves away from the origin. So if you imagine extending this into 3 dimensions, which basically is just you have 2 angles and a radius, then the 2 angles can be in our 3D texture. We can have, say, along x and y can be the 2 angles, and then z can be the radius. And that means that as we go down the texture, the radius is increasing, which means that we have that important property of as we're further away from the point, then that axis gets bigger, if that makes sense. So we can still do, if we're going to build point shadow, which is building a shadow map for the points, it's a little bit more complicated, but we can still just have that loop. That basically, in this case, is just going to loop away from the point line. Yeah. So that's actually what these artifacts around the outside are caused by, which is just this is out of bounds of that map. But if I come down here to point light, you can see there's this, say, max radius, and that's the quantization. So basically that's it. We have our 3D texture, and along 2 of the axes are the 2 angles. And then along the z-axis is the radius, which means that as we move away from the point, the z-axis is going to increase. And I mean, that's basically it for point lights. So by combining a directional shadow map, a directional deep shadow map, and then a point deep shadow map, well, we get something that looks like this. But of course, we're still missing the multi-scattering. But I'll just pause a bit there. Are there any questions about that? Because it is a little bit complicated, and I'm not sure if I've explained it particularly well. Yeah. So I'll just show, because I can show what this looks like actually, if I just find this. Okay, so that's going to look like this. This is without multi-scattering. And so let me set the camera back. So that looks like this. Yeah, well, okay. So, I mean, feel free to ask questions about that if you feel like you're not understanding it. I'd be happy to help. So that gives us this look. But of course, it's kind of missing some things because it looks, the clouds, I think, look a bit wrong. They're not kind of reflecting the light how you'd expect. You can kind of see that here. They're direct because they're being lit straight by the light, but there's no scattering going on. As opposed to this, where you can see everything looks a bit softer. Because the light is actually scattering inside the clouds. Yeah. So before I go into how the scattering works, I guess I can talk about a bit how the cloudscape here is actually modeled. So like, you know, how this is actually shaped, how we get the kind of shape in order to achieve that goal. So as I mentioned before, this is based on this picture, which I was kind of working on. So basically I was just trying to copy the shape of the clouds that you see in here, which ended up being by, well, basically what I did is let me just find where it is. Yeah. So I'm just going to restart the program so that we can regenerate the shadow. So as I mentioned, the density, that density map that I talked about, and the directional shadow map, they're both computed before. Well, that's kind of fun. So they are both computed just at startup time. Because they don't actually change, whereas the point light is computed because position of it does change, so it is recalculated each frame. So this is basically the shape of the cloud. So the way that I modeled the clouds was by building a shape that was roughly kind of, this is kind of the thing that I want, and then adding noise to it. So this is the code for that. Basically, we have, you know, a function takes on a point, returns a density. And it just does a bunch of things to just basically carve out these primitive shapes. So there's kind of this curve that kind of goes along the bottom, and it gets a little bit higher up just because that worked well with the perspective. There's a flat plane on the top, which is to kind of block out most of the directional sunlight from hitting, because I wanted it to look dark, like around this part here, mostly. And there's a back plane, which I think is actually off the edge of the area that's being rendered. And then there's also just kind of a bit of like extra density here to kind of give some more, I guess, glow to the light. So you sort of see a little bit of stuff in the air, if that makes sense. Whereas if that was empty, you wouldn't. Yeah. And then, so basically what we do, and it's really, really simple, is build these shapes and then shift it with noise. So in this case, we're using FBM noise, and we literally just take the position, and then add a bunch of noise to it. And that actually works pretty well. So if I restart again so that we regenerate, I should really have the switch for turning that on and off, but whatever. So what we've done to basically get these cloudy shapes is adding this FBM noise. So offsetting the position with the FBM noise before we actually do carve out the shapes. And that actually gives quite a nice cloudy feel. But basically the whole idea there is, instead of just using some kind of noise to generate the density, we decide on the shapes we want and then perturb those by some noise. And that tends to give a better look. However, side effect of that is that it you can't really tell. If I reset the camera, you can see. Oh, hang on, I've got stupid. Sorry. Yeah, velocity. Neither did I, but it works quite well. I mean, obviously, you know, it required a bit of fiddling to get the constants right and everything. So here it is. Basically, we have our basic planes, and we adjust it by noise. And if you look really closely, you might be able to see one of the things that this does mean is basically that for the most part the density is constant. So it's either there is nothing there, or there is something there, which is there's nothing here. I mean, there is, you know, there's that extra little bit that we add in just to get some light, but there's nothing there and there is something there. So it's just straight 0 to something, 0 to 10 or whatever. And if you look closely, and maybe you can probably see it a bit when, like here, it actually gives these sharp edges. And the reason behind that is just that the volume that contains the density here, and also the number of steps that we can take through the density, is limited. So in this case, I think that the volume is like 256 by 256 by 256, which is already quite high. And you know, you can see kind of flickering here. We can only take a certain number of steps through that. So we get basically this discretization along those points, because it's either there is nothing there or there is something there. If, say, the ray only passes through one place where there's something there, then it's going to get like this kind of outline, or you're going to be able to see, because someplace it will be there and someplace it won't, but there won't be any fade between those. It looks quite bad. So literally all that we do to fix that is, when we're generating the density map, we blur it. So add some samples from just around the points. And that actually works really well. Like, you don't really lose many of the details, but it kind of gets rid of these ugly looking like edges that you get like here and like here. Yeah. Cogito, are the occluded closer clouds solely lit by the point light, or is there GI? So there's the point light and there's also the directional light. Some of the directional light does leak through, so you can like see that's kind of how it's colored. There's also some ambient light that's added in, which is just kind of this dull blue. And then there's the scattering, which helps a lot. So that's basically, I guess, an approximation of GI, but I'll go into that in a little bit. I'll just restart this again so we get the new. Oops. Right. So that's that. Now, as I've said, that works pretty well, except the clouds just look too flat. And that's because we don't have scattering. So to introduce scattering, it's now time for my new segment, which is called Top 10 Cloud Rendering Secrets Revealed. That's right. That's right. That's right. Number 10. Burger King foot lettuce. The last thing you'd want in your Burger King burger is someone's foot fungus. But as it turns out, that might be what you get. Okay, we're not doing this. Okay, so multi-scattering. We blur the shadow map. That's it. So if you remember, we have our deep shadow map, and that is basically the intensities of, or how much light contributes to each point. We approximate multi-scattering by blurring it. And that's pretty cheap. And also totally fake, but it actually works really well. Yes, you're never going to know the secrets. So basically what we do is we have our main shadow map, which is the ones that we've generated from the lights, and then we use mip mapping. Or we basically have a bunch of mip maps. So, you know, half resolution versions of the map. And we generate those, and so each one is, you know, half the size, and for each one, we downsample and we blur. So we have our deep shadow map, and we have a bunch of, you know, downsample or downsized versions that are all blurred a little bit more. Not very much, just a bit. And then we can coalesce all those back together by weighting each of them. Yes. The Australian government doesn't want you to know. So it's actually really, really similar to how we're doing Bloom, which is take the image, blur it, downscale it, blur it, downscale it, blur it, downscale it, and then add all of the downscaled passes back together with different weights. So, except I believe it's weighted the other way around. But for our deep shadow map, we have each of our downscaled Bloom textures, and then we weight each of these. So the full res non-blurred has the most contribution, and then each of them has half contribution after that. And that is literally how we get it to look nice. So this is a shader basically. So here, okay. So the way we actually do it is a little bit different, but basically we have our directional light and our point shadow, our directional shadow map and our point shadow map. We combine those together into a light map, which just has X and Y or R and G components for the directional light and the point shadow. And then we run this downscale pass here, which is just doing a really light Gaussian blur as it downscales. And then we use this coalesce pass, which for each of those, I guess, cells in the 3D texture, it's gonna pull back each of the shadow maps. And then when we actually go to render, we can just sample from this light map. And that basically gives us an approximation of multi-scattering that works really well. So yes. So yeah, so does that make sense? So basically, so multi-scattering, in case you're not exactly aware what that actually is, because I just realized I haven't actually explained it, is basically just how you have, your photons, when they come from some source of light, say the sun, they enter the cloud, and then because of all the particles in the cloud, they kind of get bounced around everywhere. So most of those photons are probably going to be directly reflected off and go into your eyes, the ones that you see. But some of them will have gone in, bounced around a little bit, and moved, and then they'll come into your eyes. So that kind of softens out. The clouds, and you can actually simulate multi-scattering, but it's slow. So just blurring the shadow map is actually quite close to what it is, and it's not perfect, but for our use case, it works really, really well. Nobi, yeah, I know, I derailed the chat, but it was funny, even if nobody knew what was going on. Kagito, so deep shadow maps, I believe they're pretty standard for this sort of thing, because they're a very, very easy way to get extra performance out of volume rendering. So as I said, the naive way to do it, which is just march to the light for each point, is really slow. So deep shadow maps are definitely the common approach. The approach to actually blurring the shadow map I got from watching a presentation done by Smash of Fairlight at SIGGRAPH last year, I think. He did a little mini talk about the clouds in Wonder, which was their demo at Revision last year. And they did a similar approach, although I'm not sure they quite did it on the same level as us. But I'm not entirely sure. But basically, the general approach was just blur the shadow maps, and that gives you a decent approach to multi-scattering. But yes, yeah. Luna, yeah, exactly. So you could, I guess, apply if you had, if you have a big opaque occluder, then you get light bleeding. And I mean, you could always do like multiple shadow maps, one that's not blurred and one that is, but that's just a bit complicated. Like in our case, we don't even do shadows of the rocket on the clouds because you wouldn't really end up seeing it, I think. Or you might, but it didn't end up being important enough. That kind of part of the cloud's occluded anyway. But yeah, you're totally right. So it doesn't really... It works really well if you're just rendering a bunch of clouds. But if you're not, then it's not. But you can see, so in this performance kind of thing here, this part here is basically for our shadows, or for our density rendering. This is building that point shadow map, which is actually quite slow because I think it's quite high res map. Building the light map, that's combining our directional and our point maps. Blurring the light map, as I said, that's how we approximate multi-scattering. Coalesce, that's then combining all of those back together. Rendering objects, that's just rendering like the rocket, and then rendering the volume is marching through it. So overall, that ends up being, what, 9 milliseconds, which for a game, it's probably quite slow. For a demo, it works really well. Hey, Slurpee. Cool, good to know that answers the question, Kugio. Yeah, so, yeah, okay, so I think the next thing I was going to talk about was, because Luna asked about how we're reversing the fluid simulation, which I'm guessing is referring to the rocket exhaust. Yeah, let me just turn that down. And the answer to that is, it's not a fluid simulation, it is a cone SDF, or sign distance field. So the rocket in the whole demo is rendered with ray matching. So we have a distance field for that, which it's basically just a bunch of cylinders combined together. and the exhaust is also ray marching. If we go into there's a lot of shaders and they're really badly named. I believe it's this one, Rocket Cloud Scene. Here we run the rocket, and here are the jets. If I remove this, whoops, I remove this, suddenly they're just cones. So this is literally FBM noise modulating the radius of the cones based on the time or the height of the rocket or something. Yeah, so it's just based. So the height of the rocket is fed into that and offsets it. And for what we're doing, I think that works really well. I was hoping to do it as part of the. I guess I was hoping to do kind of a similar thing, but actually have it as part of the volume so that it would look volumetric. But the resolution of the volume is not high enough for it to really look good. And it was a lot of effort to kind of integrate multiple volumes inside each other. So I think this ended up working quite well for the effect that we were trying to achieve. And I guess because it's so bright, it doesn't really matter that there's no details in it. Yes. So that's how that's done. And that, I suppose, is that scene. Are there any more questions about this particular scene? I'll go into the post-processing later because that's kind of among all of the scenes, and that'll be interesting to look at. But first, we'll go through the other bits. Cool. So let's have a look then at this scene, which I think is probably the second most interesting, maybe. Probably not technically, but still. So this scene, I also model up a picture, which I mean, I nearly exactly copied it in this case, but it's this picture of the space shuttle returning to Earth. Yeah. So, as a couple of people have pointed out, Cooper was kind of mad about this, but if your rocket is pointing this way, this far away from the Earth, you are not going to space today. Because rockets don't shoot straight up, they curve. So this is actually completely wrong, the way that it's facing. And even I'm pretty sure that the boosters would not be separating this late. Kogito, do you do shaders professionally? Not at the moment, no. I did work at a video editing company where we did them, but that was very different to this. Most of this I'm completely self-taught. But yeah, so this is completely wrong. But just, we took some artistic license for that because having the rocket pointing back towards Earth wouldn't make much sense in the context of the scene. But basically, this scene, there would of course be several ways to approach this, which I thought about. One of which might be the obvious one, is to actually render like, you know, a plane here and then do some like fancy skybox stuff, or even proper atmospheric scattering equations and things like that. Kind of like what they did in Fermi Paradox. That was, as far as I'm aware, all like physically based. And that's a really good 64K by Mercury, which I'm pretty sure Cooper mentioned that they actually took inspiration from the same shot for some of it, which was cool to hear. But basically, all that we do is, this is a linear gradient. So if I just go here and do this, it's just a gradient of colors. So I can like screw around with the colors all I want. So there are a bunch of colors. Each of the colors has, you know, a length and kind of a curve value. Exactly, Daniel Collin. That is exactly it. Each of the colors has a curve. I mean, obviously I've kind of messed it up now, but for this curve here, if I reset it, if I just kill the program and restart it, then I can go back to what it's meant to look like. Okay, so it's a linear gradient, really simple. For this bit here, where you can kind of see there's a little bit of subtle noise, which again was copied off. You can kind of see the same thing here. There's a little bit of just noise applied to that. For this kind of plane here, which I guess is kind of meant to look like cloudy surface of the Earth, that is just some noise. Again, it's kind of got the position fed into the noise is adjusted to make it look kind of perspective correct, sort of. But it's basically a noise used to generate a normal map, and then that's got lighting applied to it. So if we go to gradient scene, so then there's, oh heck, yeah, you can see it derps out quite a lot when I move the camera around. That's about right. So we obviously have the rocket, which again is just remarched. But the important bit is here, this light sky function, which takes in the direction of the ray and returns a color. And we loop through all the gradient curves to calculate the gradient. Do things like adding streaks. So that's for this curve here, where it's kind of got these streaks. I think this here is, yeah, so here we do some like perspective adjustments here, which just kind of make the perspective look somewhat correct. And then there's this cloud normal function which uses this FBM noise and to calculate a normal, and then we do basic lighting on it. So it's completely fake, is the general thing, which is totally fine because we don't need to see any more of the scene than this one shot. You can see, like, if I zoom out. So it doesn't need to be, like in a computer game, right? You couldn't get away with this really, because the player is interacting with the world, and so they need to be able to look around and see things. Whereas in this case, it's just this one shot, so it doesn't matter. And that's one of the really cool things about demos, is you can get away with this sort of thing. So I mean, yeah, then we have credits, which is just text. Cool. So are there any questions? Fake it and then make it. Yeah. Cool. So why don't we now go to the starting scene, which is the clouds, or the sunrise, sorry. And this has quite a lot in common, you probably noticed, with this kind of scene with the rocket launch, such as the clouds in the sky and the God rays that you can see. But basically, let's kind of just, we can look around. This is a big rectangle. It's a big polygon. It's just, I believe, in a vertex shader, if I remember correctly. Terrain.ps. So this is just a really big rectangle with lots and lots of subdivisions in it. And then in a shader, we have a basic height map, which again is just some FBM combined together. And we just adjust the position by that. And it's simple, but it works for what we need. For these God rays, the way that we do those is by rendering a directional, a shadow map. So again, the sun is a directional light. What a common approach for shadows for directional lights, and I guess point lights as well, if you use a cube map, is to render from the perspective from the direction of the light, use an orthographic camera. so a camera where you don't have any perspective, so everything's flat, and render kind of the depth. And then when you actually want to shade each of your pixels, you can look up that and kind of see, is there something in front of me from the perspective of the light? If that makes sense. Here we're doing exactly the same thing. So we calculate a shadow map from the point of view of the light. And then in order to render these guide rays, we just kind of step through space and see, is our current position occluded or not, which is in this guide rays shader. So yeah. This isn't particularly well optimized, but it works perfectly fine for us. So yeah, it is quite slow. But yeah, so basically, again, stepping through the world, doing a very kind of similar thing to the cloud rendering, except it's a constant density. And at each point, you can see here, we sample from this shadow map, which is going to be the closest thing that the light can see. And then if we're in front of it, or if we're behind something, then the light intensity is 0. If we're not, then it's going to be 1. And that's it. And I'm pretty sure that's a pretty standard God rays approach. The alternative is you can do it as a post-processing pass, but this worked for us. So then we have the clouds. And again, more volumetric rendering. Largely the same as other things, except clouds can be a bit different. Because, say in this scene, we've got a really constrained space that we're actually rendering. So we know exactly how big it is. And that means that, we can set up like a deep shadow map over the area we need. We know exactly how far we need to march until we can stop. For the sky, that doesn't work so well. Because it goes on for a long time. So it's a lot harder to do those kinds of things. So in our case, this was actually one of the last scenes that we made. So it was kind of hacked up pretty quick. But we basically ray trace to a plane that says this is the bottom of the cloud layer. So we analytically find where we can start marching, where we can end ray marching, so the top of the cloud layer. Step through that, we have basic density function, which is, again, a bunch of FBM to generate these clouds. And at each of those points, we do a very simple version of that kind of naive shadowing approach. So then stepping towards the light to get a bit of shadowing. And that, again, is really slow. And that's the reason why this scene is actually quite slow, because the cloud's taking up all the time. And I'm not too happy with that, but we didn't have more time to fiddle around with it. But we're only doing a few steps, so because they're so far away, you don't need so many steps to render it and have it look okay. So yeah. Yeah, so I mean, that's basically that scene. I feel like I've kind of gone over it pretty quickly, but I'm not sure kind of if you guys want more detail on what parts and everything, but please let me know. Yeah. So initially one of the things that I was working on for I guess this scene slash this scene with the rocket is reflections, because one of the first things I wanted to do here was something like this shot. So like a kind of river there, and then like some details of things in the rocket taking off in the middle, because that would look really nice. But so I was working on screen space reflections, which, so basically you trace from a point into the world. But it didn't end up working very well, and it was really hard to get kind of the amount of detail in this that you needed to make it look decent. So instead we went with the approach of, have some kind of sunrise and then have a really... So this scene with the rocket here is really basic. It's 4 of these pylon things, the rocket in the middle, and that's it. You can see the clouds dumping out, and I'll explain why in a minute. So yeah, really, really simple stuff. And this scene is, again, so we use the God rays here. It's exactly the same approach as before. But, you know, with some positioning of the map, of the shadow map, which is why it looks a bit funny when I zoom out. So these pylons, they're meshes. So one of the kind of things you might notice there is we have the rocket, which is ray march, and we have the pylons, which are meshes, and we also have like the smoke that you see like here, which is, I guess, ray march as well. Yeah, the spaceship's turned off because it's slow with the shadow maps. Yes, the spaceship's missing. But you can see there's smoke there still. So these pylon things, those are meshes. So we're combining, say in this shot, there are 3 different rendering approaches. There's meshes, there's the rocket, and which is sphere tracing, and there's this smoke, which is ray marching, which is actually not that hard to do. Basically, you just are using the depth buffer. For meshes, it's the everything's normal for like the normal way you'd approach it. For sphere tracing, you can write into the depth buffer, and then you'll get that will just work. Are you drawing a bounding box for the rockets? I don't think there's a bounding box for this case. Yeah, I was kind of considering doing that, but it ended up being easier to just disable, like have it not disable that pass for the shots where you can't see it. Like there's a switch, I think. Rocket, yeah. That's gone. That's there. That's gone. That's there. The softness on the direct light shadow on the rocket, just the blurred shadow map. Like softness on this shadow here. There are actually no shadows used. So that shadow map that we generate, we don't actually use it for shadows, because there isn't really a case here, for the most part, where you would see shadows. Except possibly that could fix that. But yeah. So the lighting is a standard PBR kind of thing. Yeah, with there's some ambient light in there as well, but not very much. So if there isn't any ambient. Whoa. Yeah, that's the ambient light. But yeah, so this is just direct. There's no blurring of shadow maps in this scene whatsoever. We do use a deep shadow map again for this smoke coming off, but we don't do any of the fancy blurring of it in this scene because it's so light, it doesn't end up making any difference. Like the shadowing itself doesn't make much difference, but it's nice to have. Yeah, so we got polygons, we've got ray matching, we've got ray matching, we've got polygons, we've got sphere tracing, we've got ray matching. For the clouds, again, it's the same approach as we use here, like the same code, except in order to save some speed, one of the things we do, which you can notice here, is since based in all these shots, the camera never changes direction. The camera never changes direction, so we can just generate these clouds as a big texture for each of the shots beforehand. So up front, start of the demo, during the loading screen, one of the things is generating each of these. And actually in here I can go down and there's a switch for Gen once and live. So if I set this to 1, now they can generate it live, and you can see they're really, really slow in this shot. But now they will respond properly. If it sets back to 0, now they're stuck again. How does the objects in the property editor mesh with the shaders? Does each one just have a... Oh yeah, so I'll go into that, how that works in a little bit. I'll just finish, I'll finish going through the shots, and then, yeah, then I'll go into a little bit more about how the code works. But basically, each of the generator clips is backed by code. So that code has the option of running a shader and passing the properties in if it wants. It doesn't have to. Right. So the fluid simulation here we do is a basic grid-based fluid sim. You can find examples of this all over the internet. Using a bunch of compute shaders, so these ones, there's quite a lot actually, but it ends up working pretty well. Again, that ends up becoming a density map, which we just trace through in exactly the same way as the other things. Yeah, so they're statically bound at compile time. The properties, yeah, the properties are static. And I'll show exactly how that works in a minute. Yeah, so fluid sim. One of the nice things about that fluid sim is it's simple enough that you can actually really easily do collision against objects. So here you can see the clouds can't go into this kind of bottom area. It's a bit bright. I'll see if I can turn down the exposure. And that, so one of the fluid sim methods I was looking at beforehand was like a particle-based one, which was like a Vorton-based thing, which preserves kind of the details of the motion a lot better. But it tends to be, from what I could tell, really quite a bit more difficult to actually enforce kind of boundaries, and you also don't quite get kind of this volume look. But so this is a really simple fluid sim. It runs quite quickly. It does what we need it to do. Yeah. And you can see in this case where we're using that kind of point light shadowing again. So there's a point light in there, which is the rocket thing, and then it's casting shadows out over this area, which works well. Cool. So, I mean, I feel like that's basically all of the actual parts, all the scenes of the demo. In summary, there's a lot of volume rendering, and everything else is really not that complicated. So actually, yeah, so let's go into how we do like color grading and everything first, because I think that's a really big part of the demo and getting the look that we want. So in the timeline, we have a grading clip, and we have one of these grading clips for each shot, because all of them are slightly different. Basically, the key things that we have are, we have our camera controls and like vignetting, a slight chromatic aberration, just gives, I guess, a bit of color around the edges, a little bit of grain. We have bloom, and so I mentioned this before, but the way that we do bloom is downscaling and blurring a bunch of times, then adding those back together with different weights, and that gives like a really nice bloom. And it also means that we can adjust the shape of the bloom by adjusting the shape of the blur, which we use, say, here to get this kind of wide thing. So if I change this, I don't have the right one selected. If I change this, you'll see it'll change the shape of the bloom. So we can get like really, really wide stuff. But the wider you get, you start to get a bit more artifacts from the downscaling. Yeah. So we have bloom, and then we also have the tone mapping, which we can change there, but we don't. Now the really, 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 really important thing, and this is something I think I learned from a blog post that Guy of Conspiracy did at one point, which he learned from Zoom, is color gradients. And this is a really, really important part of the demo. So basically on every single shot, we have a color gradient. And that's just from like some point on the screen to another point on the screen, it's just two colors interpolated between them with some mixing amount, and it's just like an overlay. So if I turn this up, I guess that starts to look a bit funny, but basically everything is tinted by these colors we have selected. So like in this case, we have this, I guess, like light blue and like a pink, and so there's like the light blue is up there and the pink is kind of down there, and that gives us this gradient on here. Without that, it looks like this, which is really plain. So basically the approach that we take is leave the scenes for the most part without color, and then add the color back in with the color gradient. So if we look, say, like at this scene here, I turn this to 0. Actually, that's probably a bad one to demonstrate. This one's probably good. No. Oh, right, I don't have the right clip selected. There we go. So 0, it looks like this. The colors are all blown out. It's kind of grayscale. It looks kind of ugly. But by adding in this color, so we have like a gradient from, so like over here it's kind of red, over here it's blue. You can imagine like the sun is in this direction. So we have like a warm color here and a blue color here. Just adding that, you know, adds so much more. And well, that's another good shot. So like here as well, if I, you know, no color, color. Yeah, and so that is just one of the really big things that gets that look. Again, just get that up. Again here, right? So much difference. And I don't think this. Yeah, this one here doesn't have a color gradient because it was already done. But yeah. Yeah, so I mean that's basically it. As for kind of post-processing pipeline, I purposefully went for a really minimal post-processing setup for this because I think it helps with the look. Like, as people have said a lot before, you know, the way that you design your post-processing pipeline is, you know, contributes to the look that you're going for quite a lot. If that's probably a really bad way to say it, but you get the point. So in our case, we're going for a really simple kind of thing where we're just showing like the important things. So like we have a sunrise. It's a simple scene. We have this rocket thing. Again, it's really simple. And the processing is part of that. It's nothing fancy. There's no depth of field. There's no lens flares. There's no real chromatic aberration. We just have this kind of channel separation. Yeah, exactly, Luna. So you design your post-processing pipeline for the kind of thing you're going for. So if you're going for like a Logicoma style thing, or I mean not a Logicoma style thing, but just like a general music-based, colorful, fast, then you're obviously going to have a bunch of effects and things that you can use to mix up your styles. Yeah. So. And I mean, going overboard with depth of field and bloom and chroma might not be bad for that kind of, as I said, like fast-paced, music-based kind of thing. But for this sort of thing, we don't need them. Here you go. I'll turn up the yeet slider. Oops, that's a bit too much. That's my chromab slider that I added in today. Boom. This must be why we didn't win the compo. We didn't have this. I'll remember next time. Yeah, check it out. Because, yeah, I don't think you guys go overboard at all. I think it totally suits what you're going for. But like, yeah, overblown chromab is definitely works for a lot of styles. Yeah, so I mean, actual demo content, I feel like that's probably it. So at this point, I guess we can dive in and look at the actual code for like the tool and how things are set up. If you guys are interested in that. You lose 3 to get to first place. Yeah, I need them all. Yeah, so yeah, I mean, let's do that if you guys are interested. Oops, here we have the code. So I mean, I guess the first thing to mention is this demo is entirely written in Rust. The tool and the player and the engine are all the same because it's nice. Yeah. So as I know Ferris has talked about this a lot about how Rust doesn't really make like it can be more, it can be harder than it's not necessarily the best choice for like a 64K just if you're coding it as the actual player, because you end up having to do a lot of like interop with C code and you end up needing unsafes everywhere. But when you've got a tool, that's where the real value is. So in our case, we have our tool which is in Rust using imGUI, and then we have our engine which is in Rust, and those are kind of the two places where I think it's really nice too, because our engine is quite code heavy. You know, there's a lot more code there than maybe I guess a lot of other demos that rely on shaders. Oh, see you, Ferris. Goodbye. Yeah, so, and then just, you know, having the player written in Rust is just a side effect of making it, you know, it's easier to interrupt between the two. So, basically, so the way that the engine is set up, right, is, or clips that we can have on the timeline in particular, is each of these clips is struct. So, say, this is kind of the cloud scene, which, oh, we don't actually use that one. Let me find that one we do use. Go to the hill scene. Skip that. So this one's really simple. We have a hill scene, there's a trait for that, and then we have this list of properties. This is a really bad way to describe properties. I'm not happy with it at all. But basically, we have, just ignore all of these. We have a list of groups, and each of those groups has properties, and then in the actual code, we reference the properties by an index. And so we get this input list of properties, this input array. Actually, if I go to code, we have this properties list, and then there's this prop function, and we say properties, and we provide a group index and a prop index. And that gets the property of the correct value type. So each property has a type. We can have like, we can have floats, vectors, colors, rotation, which is a quaternion, and references to other clips, which we didn't actually use in this. But yeah, so then the animation system basically just works in these properties and sets the values in these arrays before each clip is called. So each clip has an update function or method, and that's just called from top to bottom in the timeline with, you know, like some context, which is just a bunch of stuff, a list of renderers, and renderers are just kind of pre-made like things that do something. So like there's a chromab renderer, there's a clouds renderer, there's a distance fog renderer, there's a DOF renderer which we don't use, there's FXE renderer, there's God renderer, etc. And then the generators actually just use some of those renderers. And this demo is Rust and DirectX 11 because I wanted to try DirectX 11, which is why this is not OpenGL, this is DX11, and that's also why we were using HLSL shaders here. Yeah, so I mean, structure-wise, that's mostly it. So we run each of these generators from top to bottom in the timeline. As part of this context, they have a no, not part of the context. There's this I/O, which is a G buffer. It's not actually G buffer, I guess, but it's we have like a bunch of textures, so like the scene, the normal map, the world position, depth buffer, and each of these generators is provided with that and some other stuff, and the generator can do whatever the heck it wants. So if it's generating some mesh, it can, or it's rendering a mesh, it can just render it to that G buffer. If it's simulating a fluid, so there's this simulate fluid, then it doesn't, it ignores that, it just runs the fluid sim. Yeah, which is just in a shared position. So then we just have these renderers, which is kind of just like common things. So like bloom renderer renders bloom, etc., etc. Each of these generator clips, so each of these classes, like this grading effect, this struct is there's an instance of it for each of the clips in the timeline, but each of these renderers only exists once in the actual, in the whole thing. So they're created at startup. So in the engine we have there's some mesh generation things. We don't use most of this, but it's just things like, a bunch of primitives like a quad or a cube or a cylinder, sphere, blah 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 blah. I don't know. So the tool itself is InGUI, as has been said before. It's really, really hacky, really, really messy, but yeah. But InGUI makes it really easy to quickly prototype things, which is really nice for this project. Just being able to quickly make a timeline thing and then really, really easily add interactivity to it was invaluable to make it quickly, I guess. But yeah, and just kind of learning about, like, one of the really most valuable things I think for developing this tool was learning, this is how people will try and use this, especially seeing so yeah, totally, Luna. But so one of the things, so I guess I haven't really talked about how Nobi and I worked on this project, and I'll talk about the project a bit more, I guess. But so basically, Nobi started off doing the music, and I was doing all the graphics, and then as things I think got close to the deadline, Nobi was a bit interested, I think, in helping with some of the graphic stuff. And at the party, basically, he ended up doing a bunch of like editing work. So we had a bunch of spaces in the timeline that didn't have clips, and he kind of went through and filled in a bunch of those things, which was awesome. And it was just really, really cool seeing him use the tool, or them use the tool. Sorry, I keep saying him. I apologize for that. Using the tool, and just seeing how somebody else uses it, and kind of learning based on that. And I think that's really invaluable. But yeah, I don't even know what I'm talking about at this point. So that was really cool. I was really, really happy with how we worked together. I think it worked out really well. Like, we were both on the same track, I think, the whole way. He would kind of, they would kind of provide, a track, and we'd kind of about, we could do this, and this would kind of work, putting in the countdown and all that stuff. Yeah, exactly, Luna. Thanks, Nevi. I kind of know how I want to iterate on this now, which is really good. So stay tuned for the 64K clone of Notch, coming soon to a demo party near you. Yeah. So yeah, yeah, it was really cool. Working together, it worked out really well, I think, which I was very happy with. But yeah, and so I mean, the idea for the demo, we started off like, I started off. I was like, I want to just do something with rockets because I had this scene of a rocket. I had this kind of thing that I was working towards, and then it kind of evolved into like rocket launch, and then kind of this like imagining like it's from the point of view of somebody involved in the rocket launch and like kind of this like how they'd be feeling looking back, or kind of the way that your mind works in that kind of environment. And so that kind of suspenseful but on the same line, I guess, like beautiful sort of thing. I mean, I'm pretty sure that the very first pitch that I sent was just, here's a scene I've got. My plan is just to make a bunch of nice looking shots and put them together. Which I think doing a rocket demo without the rocket at all. Yeah. But yeah, so I didn't use rocket. Which is actually so the thing that I learned from my previous intro, which I did in 2017, was that rocket is just didn't end up working that well, at least for me, with like cameras and just like 3D stuff. So I really wanted to try out just working on like a proper curve, like keyframe editor, where you can have like curves and things and you can see them visually, which I think this way worked out pretty well. So having like this kind of space, like I can adjust keyframes and move things around. But yeah. So I mean, yeah, I know kind of now like what the annoying things are with this and how we can improve it or how I can improve it next time. Which is, yeah, as I said, really invaluable stuff. Yeah, exactly. Like Rocket is really good, I think, for like it's just something you can really quickly drop in to your project, and then you can just like set up, get going really quick with it, and like yeah, like if you don't have like a tool, you can just integrate it with your exe and work on it, and everything's fine. But it gets to a certain point where, especially working with like 3D things, just gets to be a massive pain. And one of the really valuable features that we had here was that, so here we've got our camera positions. What I can do is I can lock these off, which means that now I can here I can move the camera around, and I can find a new camera shot. And if I can't find a camera shot, I can uncheck these and it'll reset to what the animation curves say. But if I do, then I can go around, I can find a camera shot, and then I can hit these buttons. And now it creates keyframes from it. And that's one of the things that you can't do with Rocket, because you don't get kind of feedback from the app back into the editor. Is you can't have it so say like you can interactively move the camera around and save that position. Aaron, Slurpee, yeah, it does a bit, I guess. It was kind of modeled. It's a little bit after, I guess, probably more so Premiere. But yeah. Yeah, so that's one of the really nice things I think about having the animation system built into the tool, is that you can have like the feedback between that and the rest of the tool, which is invaluable. Just also being able to have like separate clips down here, and you can, like, if we wanted to move a shot around, if you want to do this in Rocket, it's pretty difficult. But if I want to do it here, I can just I can move it around, and that is insanely useful for a lot of things. Being able to just visually see and move around the timeline. Yeah, so I don't really have much else to talk about. the only poo brain through it. Yeah, so I'm not so again, kind of like with Rocket, ImGUI is like, you know, a tool for really quickly prototyping UIs and making something in general, making something that's just like quick to set up, and quick to get working. But after a certain point, I think it gets to something where using a proper like retained mode UI system like Qt or WPF or something is a lot better. And this is basically probably at the breaking limit of what I would do with ImGUI. Because, for example, one of the problems we had when I was working with Nobi at the party, is that his laptop or their laptop couldn't render the thing at 60 FPS, even with a reduced. So we reduced the resolution so we could, you know, watch it, but because the whole UI is tied to the frame rate of the preview, if you go and try and like change values and stuff or move the scrub around, the UI doesn't respond at 60 FPS because the actual rendering of the timeline is blocking it, which is yeah exactly maybe yeah. So I'm really glad with the timeline that we could do that, but yeah, so that's one of the problems with ImGUI, yeah, is that because it's all tied to, you know, like rendering through the same, I guess, pipeline or whatever, you can't interact with the UI at 60 FPS if your project isn't running at 60 FPS. Yeah, that very possibly, and that might be an approach. I think that I would kind of prefer to, for a bigger project, to go with a more mature UI system anyway. Just because, like, I guess you get a lot more batteries included with that kind of thing as well. Like with this, you know, there's a lot of hacking around layouts and stuff and custom controls. Yeah. Whereas like the kind of more mature UI systems, it's often a bit easier to do that, if that makes sense. But something like WPF, say, the nice thing about that, if I was to do another tool that was DirectX, WPF directly integrates with DirectX, so you still get that easy thing where you can still embed DirectX stuff in, but all of that, like handling of, I guess, separate threads, gets handled for you. Yeah. But yeah, so that's, I guess, what I think. Yeah. Yeah. Yeah, so I imagine threading could help, but it's not really something I wanted to look into for this. I think it would be a little bit of a pain. I mean, Rust obviously makes it a lot easier because that's one of its design goals, is to make threading safer, so you can do it without needing to worry. But yeah, it's for a quick tool, something I want to worry about. Colin, I think that there's a branch that they're working on with like the so this docking system I pulled out of a branch. It's not actually in master, but it also has this like multi-viewport system, which the idea is, I don't have it running in this tool, but the idea is that you can like take a docking thing and snap it out, and it will be a separate window that you can move around. So like put it on different monitors and stuff. And I'm guessing as part of that, they would support more than one context, but I haven't looked into how that actually works. Yeah, the demo window has the same title if you're on the 64K. Yeah, I was waiting to see if anybody noticed that, and then Luna messaged me last night and was like, "Damn you!" Yeah, I was waiting for somebody to find it. But yeah. So yeah, Oh, that's a lot of chroma. Oh, does it? Luna said, I only noticed because it shows up in the render.ui when injecting to the process. Great. Yeah. Super laggy. Yeah. One of the things I found from this is how much fun it is to play around with fluid simulations. Like this kind of thing. Obviously it's not running at the moment because we're not playing back, but if I... That's really, really loud. Like, fluid sims that you can, you know, like, one of the really important things for tools I found, or just making demos in general, is just having the ability to have a bunch of properties in a UI that you can see them all and you can just fiddle with them, like, and color pickers as well, like, and so you can just, you know, say fluid wherever it is, fluid sim. Here I have this position. I can change where the fluid is emitted from. And you know, I can just fiddle around with this while watching what's going on in here and just playing with the properties. And I think that's invaluable to the creative process. And that was one of the ideas behind, you know, making the tool in the first place, is not having to fiddle with code. Yeah, because at least for me, I find that when I'm working on like creative stuff, I don't want to have to constantly take breaks to go write a bunch of code or like debug why the heck my screen is black, or white or whatever color, or just not working properly. I just want to be able to focus, like sit down and fiddle with things. Which obviously this doesn't quite get to that goal because there's still a lot of code required for each of these like clips, but it's certainly a stepping stone. Yeah, exactly, Luna. And I think that having just the ability to have a bunch of things you can fiddle with, like, and just get interactive, so immediate like responses, is a crucial part of that. Yeah, what Tanaclon said, UI is always the worst part. Yeah. Yeah. So I mean, like I've used Qt and for the synth that I've worked on, and it is a bit bloated, but I quite like it actually for what it is. And WPF as well. I think it's similar. Guardian said, CPDG, how are Rust bindings for ImGUI? So there are mostly complete bindings. There's a project. Let me look it up. So there are these bindings which I used in a previous project. The problem that I found for that though is there's a bunch of things they don't support that I had to go in and add support for. Especially in this project where I'm using like this docking thing, which was in like a custom project. Anyway, there are a bunch of little things that I found when I used this that I had to kind of add in support for, and it ended up being a big pain, and there was stuff like that. So this is really, really great for if you're just doing the regular ImGUI stuff. But in this project, I just used the C bindings, which ended up being fine because that's mostly constrained to like the big messy UI parts of the code, which are bad anyway. Yeah, so there are decent Rust bindings for ImGUI, but they are missing some features. But they are all right. Luna, yeah, live reload is definitely another incredibly useful thing to have. Yeah, and also along that line, I guess, like this tool has shader live reload and also like shader includes, so I can have like this shader and I can include another shader. which when you're doing this, like, I guess complicated things where I've got a lot of these shaders for like fluid sims and volume sims, and they all share things and stuff, that helps a lot, because then I don't have to like copy and paste stuff or whatever. Yeah, but that can be a bit of a pain to set up. Yeah. Did it integrate? What brings that in? So in HLSL, this is actually built in a way. So the DirectX compiler that you call you can give it a callback, basically, that it will call whenever it finds an include. So with like GLSL, what I did for my 64K back in 2017, which was OpenGL, was just use like a regular expression to find all the includes and then replace them and stuff. But HLSL actually does that for you, or the DirectX compiler, so you can just give a callback and handle it, which makes it really, really easy to do. Yeah. And so like in the actual player that's distributed, it also uses this include mechanism, although it replaces the actual names with like an integer ID for the shader code. But yeah, so it's quite easy to do. Yeah. So I mean, yeah, as I said before, I don't have much else specifically that I want to talk about. So I mean, if there are any other questions, that'd be great. Otherwise, we're going for an hour and 50 minutes, which is quite a long time. So you could probably wrap up soon if there aren't any more questions. Okay, Poro, you may ask those many questions. Guardian said, what about GLARB shader language include? I didn't actually know about that. I guess that's what, alright, so I guess you can add. I didn't actually know about this, but seems useful. Yeah, it'll be interesting to see if this is actually common. But either way, like doing it just the regular expression way or whatever, and finding all the includes and replacing them isn't particularly difficult. I mean, it's not really hard at all. So yeah, like there's nothing wrong with that. It's just one of the nice things about, I guess, DirectX is that it'll do that for you, which, yeah. Right. So, I mean, are there any more questions? I guess not. In that case, we might wrap up for today. If you want to talk to me or ask me anything else later, you can always find me on Twitter or on IRC, on the revision channel on IRCnet. That's where I most commonly are. You can email me. I think there's a link in the Twitch bio page thing. Yeah, you can message me somehow, whatever. I'm always happy to answer questions. Yeah, thank you all for coming to the stream. Hopefully you learned something. Hopefully it wasn't just my random ramblings. Yeah, thank you all very much for coming. Thank you heaps to everyone who was at revision. Like, it was awesome meeting all of you, especially to all the people in the 64K. It was a really awesome compo. And it was a really great first revision experience, and I definitely want to be back sometime whenever I can make it. Yeah. So Oh yeah, and special thanks to Nobi for doing the music and providing a lot of like creative support and editing and stuff for this. It was really, really good. Yeah, so the 4K competition was excellent as well, Akama, as was your so cute entry. It's the best. Cute little dog. For anybody who hasn't seen, oh yeah, so for anyone who hasn't seen Polarity's demo, which was Luna and Subby, definitely go watch that. It was great. That was a 64K called Brainworm. For anyone who hasn't seen Ferris's 64K or Logicoma's 64K Dope on Wax, it was excellent. Definitely go watch that. Both of them have done breakdown streams. I think Ferris's one is on YouTube, and Luna's one's probably on a Twitch channel. Nobi did on Saturday evening, he did a breakdown stream of the music from this intro. So you should definitely go watch that if you're interested in music. Oh, cool, Luna, yours is on YouTube too. Good to know. And I think Nobi also talks a little bit about the creative process as well. Yeah. Yeah, and also watch like the 4K compo. Like Akama's entry is the cutest thing you've ever seen. It's so good. Yeah, and I mean everything else is great. Yeah, so thank you so much for coming. And I will talk to you all later. Ciao.